Okay, let's start. We try to split this today's class into two parts, and with something like 10 minutes interval. So today we talk a little more about degrees. I already included the notes in our Google Classroom, and okay, a word of reminding. Every time I think I prepare more things to talk about. For example, if you track my first notes, I think there is one example or two I didn't talk. So usually I leave some stuff at the end. If there is no enough time, we will not talk about it. You can read, and if you don't have time, it's okay. You don't read it. It's I try to choose more important stuff at the beginning. So today we'll talk about degrees. So it's not a real topic. It's just after the introduction, we decided to focus a little more about the degrees, because it's a basic thing. You have to understand the graph locally. You have to know how many edges attach what we call incidental to vertex. So a degree, let's say for example, of a vertex is the number of edges incidental to it. Okay, so you just count how many edges is related to this vertex. So let's start with a theorem, which is not so hard but very important. Theorem. So the number. So we are always working in a simple graph. Okay.
Okay.
So what is a simple graph? Meaning that any two vertices, you don't see double edge or triple edge or multiple edge. No multiple edges. So it's simple. Okay. Either you have an edge or you don't have an edge. So the number of let's say the sum of all degrees. Sorry, the sum of all degrees of all vertices is even. This is a kind of simple. Okay. So and therefore the number of all the degree vertices is even. So I explain. The proof is really simple. So what's happening is that usually we can put D1, D2, D3, for example, until Dn for the degrees of, for example, we list all the vertices, V1, V2, V3, and then Vn respectively. Okay, so it's just for convenience. We have names. This is the degree D1, for example, is the degree of V1. So or dk is just the degree of Vk. Okay, so to be more precise. And what is the sum of all dj, for example, j from 1 to n? So in fact, if you sum all the degrees, you note that each edge, it has exactly 2 vertices. So you think, if you think of this, you make sum for all the degrees for all the vertices. For example, when you are considering V1, you are looking at these 4 edges. And at some point, when you are considering V2, you look at this edge again. So exactly every edge is counted twice. So this sum is always equal to 2m, where m is the number of edges of the graph. Okay? So it's an even number. In particular, it's an even number. Okay, this computation is not so hard, but it's kind of important. It involves a very major idea, which we call double counting. So we count some objects in two ways, and you can obtain some equality, or sometimes you can make some inequality them also. Okay. So the second statement says that okay, the number of all the degree vertices is even. So this sum, if you look at it more closely, maybe we can make a definition, but it's not necessary. It's because everything is very simple. Sometimes we call odd vertex to refer to a vertex whose degree is odd. Even vertex is a vertex whose degree is even. Okay, so we don't need this. So this sum, actually, you can split it into two sums. First sum is kind of all vertices such that the degree is even. You take all the vertices in V such that dV is even, and all the vertices such that dV is odd. Okay, and you make the degree of it. So you just split this sum into two parts, depending dj is even or odd. If it's even, you put it into this first sum. If it's odd, you put it into the second sum. And the sum doesn't change. It's 2m, right? It's 2m. So in particular, as we already proved, this is an even number. And this is clearly an even number because it's a sum of even numbers. This is clearly an even number. So it leaves this guy, the sum, the total sum, again, an even number. Okay? But we are summing all the numbers. So it means that the total number of vertices in this group is even. Okay? Because if we have odd number of odd vertices, then the total sum would be odd. Okay? So you have this consequence. The number of odd degree vertices is even. This is very general. Sometimes you can actually use this to prove something. I have seen many Olympia mathematical contest questions. You have using this fact. Okay, you have to use this and combined with other ideas to solve the problem. It's very simple, but you have to remember this. Okay. Given any graph, there are some restrictions on the number of even degree vertices and odd, and no restriction for even degree vertices, but there is this subtle property for all the degree vertices. Okay, so here I want to make this remark. I said it, I want to write it. So the technique here is what we call double counting. It's really important. You just count some objects, something. You count something in two ways, right? So you can think about it this: what thing we counted for twice for this problem? You can think of more as an exercise later. Sometimes it's pretty abstract. Okay, so it's actually you can describe it. So today we will focus first. I think I choose most of the things about degrees, and the second, this method. We try to use this method many times in different contexts. So you try to remember many new information about degrees and this particular method. This is today's task. So let's prove another more complicated proposition. It's in our big book. Okay, so the book of Bondi and Murdy. Every chapter, I think it has a special page. It gathers all kinds of proof techniques. So this double counting appears very early. I think it's chapter 1 or chapter 2. Okay, so I copied this example. So G is a bipartite graph. Okay, so let's write down its two parts, x and y, and we ask G to not to have an isolated point. So without isolated vertices. So what is isolated? It makes the graph a little strange. So if we have a point here V and the degree is 0, then we call this point this vertex isolated vertex. It doesn't make sense. So if you have a graph, for example, this graph, and here you have a vertex and it has no edge at all. So you don't consider at this point, you don't consider this vertex a part of the graph. So we make this mild assumption that this graph G has no isolated vertices. Okay, so there is no vertex who has degree 0. Okay, there is no trivial vertex. So we have this assumption. G is a bipartite graph and on x and y. There is a condition. Suppose that for every vertex, say okay, so for every edge xy, such that x in x and y in y, if you take any edge like this, the degree of x is greater or equal than degree of y. It's a little let's try to understand this condition. So if I observe an edge, so here this is x, this is y. So what happens is that the degree of x is more or at least equal to the degree of y. So if this x, this vertex, it induce 3, for example, edges, this vertex y, it induce at most 3 edges. Okay, so this is a local condition. For every edge this happens. Okay, so it seems, and it is correct, that this part has more vertex. Okay, does it make sense? So conclusion, the size of x is smaller or equal to the size of y. Okay, and moreover, the equality holds. This guy is an equality. The equality holds if and only if this dx equals dy for all xy in E. So this is inequality is equality for every edge xy. Then x size equals y size. I think it's natural, but the proof is pretty nice. The proof involves double counting. So I don't think it's very easy to not use double counting. Although it seems the conclusion is correct, but without double counting, I don't see a very simple way to prove this. Because if you reduce this to a sort of induction, it's endless. Probably you cannot succeed. You have to deal with all kinds of different cases. Locally, it looks like fine. Because this X has more neighbors and this point Y has less neighbors, so it seems it forces this part to be bigger than the X part. Okay, but to prove you have to make some more global estimates. It involves the double counting. So this double counting is a little more complicated. So let's write a very long inequality, okay, and using this condition. So X, this is just the sum, for example, I from 1 to I mean every let's say no, let's say I don't have name. So let's say X in X. Okay, for every X in X, I just sum 1. Are you familiar with this kind of summation notation? Is that okay? Yeah. So in the graph theory, we do this a lot. I think this part of graph theory is more, to me, is more analysis. Okay, it's if you put it into a different branches in mathematics, it's more like the branch of analysis. And there is another taste, another direction of graph theory is more algebraic. I probably I'll include several lectures about that. But at this point, it's a lot of estimates. So this is just for every sum, you put 1 here. So basically you count. And then you decide to do something very stupid. So you put the degree of X and times 1 over the degree of X. So it's a bit strange, right? And then you continue. This is you keep X in X. So this is just this product equal to 1, right? And then you decide to do this. So you make a sum all X, Y in E and the Y. So let's say for all Y in Y with the condition that X, Y in E. So basically this sum equals dx. So you translate dx into a sum. Again, a sum of ones. Okay, you try to find all the y such that xy is an edge. The number of it is exactly dx, the degree of x, and each time you put 1 here. So what I'm saying is that is dx exactly it equals y in y, x, y in e, and sum by 1. So I use this equality and replace the x by this. And this guy is 1, so you make a product with 1 over d of x. Okay, so I clean this. Okay, and I keep writing equality. So at this point, it's a little more complicated. I choose. So I manipulated with this double sum. I put x in x and y in y. Okay. I consider all situations that x in x and y in y. If they form an edge, I put 1. If they don't form an edge, I put 0. So I decided to write a function for this. So it is something called the Dirac dot function. So it's like x, y is an edge. Okay, so this notation is a little more advanced, but I try to do it slowly. Okay, and this guy 1 over d of x is kept. We don't. I just move what's inside this rectangular here. I'm saying that it's the same thing. Let's repeat. So this sum is that first I sum all x in x, and then I found all y in y such that xy is an edge. So it's a double sum, and I put each time I put 1 as a summation. I claim that it's the same. I choose all possible of x in x and y in y, but the sum sometimes are 0. If xy is an edge, is 1. The sum is 1. If xy is not an edge, the sum this I put 0. It does not add anything. So formally I added more terms, but many terms are 0. And the ones that are not 0 are exactly this one. I changed nothing. Now I use the condition. So the condition of I never use the condition so far. The condition of this proposition. So when xy is in E, so that's when this is 1. But if this is 0, doesn't matter. So it's 0 multiplied by something, it's 0 again. So when it is 1, I know that xy is an edge, then d of x. What's the condition here? D of x is greater or equal than d of y. It means that 1 over d of x is smaller or equal than 1 over d of y. Okay, so this is smaller or equal than, I keep everything x in x, y in y, such that delta xy in E and 1 over d of y. Okay, so this inequality only holds when xy is an edge of E, but it also holds if xy is not an edge, because both are 0. Okay, so maybe I speak too much. I have to, if you already follow me, so the rest will be very simple because it's symmetric. Okay, so we just return because this guy equals. Now I decide to put y first, and then I put xy x in x such that xy is an edge. Okay, so it's a symmetric, and this is dy of course, and this guy right. So I got y in y, and let me see, and this guy is dy actually, and eventually it's size of y. I got this. So this is the proof. So the size of x eventually is smaller or equal than the size of y. And moreover, if they are equal, the only place we have inequality is that our equality is here. And this guy is equal if and only if d of x equals d of y for every time you use it. Okay, so so we conclude that equality happens both if and only if for any xy is an edge, d of x equals d of y. Okay, so this is the proof. Okay, I think it's a very beautiful proof. And it involves a kind of a more complicated double counting. Okay. Any questions? Great. So we continue. We try to do some similar things. So there is a graph which kind of familiar and a little general than bipartite graph is what we call k-partite graph. Okay? So I think it's a kind of natural, a k-partite graph. It just has k parts. For example, v1, v2, and vk, and all edges. So I mean, the union of this is the total vertex set. So V will be the union of all these parts, and all edges of the graph are between parts. So let's say it means that there's no edge inside any part. So so this kind of thing happens a lot in graph theory. So people, it's very common. This always you always have to deal with this kind of graph. So basically, you have v1, v2, and so on, v3, and so on. And for example here vk, and every part has no edge inside. So all edges are between parts. So probably like this. Okay, I'm not saying that you have all the edges. In that case, you call it a complete k-partite graph. Just once you can find k parts such that all edges are between parts, there is no edge inside any part, then you are looking at a k-partite graph. Okay. For example, if you have a 3-partite graph, it is also bipartite graph. Okay, because you only have edges here, edges here, edges here, but you can also think of this is one part, this is another part. No, I'm saying something stupid. So it is also 4-partite. Okay, so you can split, for example, v1 into v11, v12. Okay, because there are no edges between them, and v2, v12, v2, v3. Okay, and it's also a 4-partite graph. By definition, it's just it's not very interesting. I'm saying that if you are not looking at a complete, for example, k-partite graph, then a bipartite graph is also 3-partite, also 4-partite. It doesn't make sense. You have to be clear what you're thinking about. Okay, so it's not very how to say it. It's not exactly. For example, you are talking about bipartite graph. In your mind, you have 2 parts, v1, v2. But it's possible you split it further this part into 2 parts, and there is no edge between them. It's happening, okay? And then you call it a 3-partite graph, okay? It's sometimes during an argument, it's just you don't know enough about the graph. So at some point, you give it a name, and you don't know everything about it. So the names are not very clear. It's not what I mean. It's not very revealing about all its properties. So what I want to do about this? So let me ask a question about a k-partite graph. So let's say we are talking about complete k-part in the, let's say, in the complete k-partite graph. There's no confusion now, okay? With parts, for example, v1, v2, let's say vk, and probably okay, probably I put ai equals the size of vi. Okay, so make it more precise. So I have k parts, and each part I have exactly ai vertices, and it's a complete complete k-partition graph. So the question is how many? It's not a difficult question. So how many edges are there? Okay, so if you think a little bit, probably I'm sure you can solve it. And the idea is that there is a simple way. So you first for example, this is V1. You count all the edges. Okay, you count all the. For example, you count all the edges involving V1. So it will be A1 times n minus A1. I'm talking about complete k-partition graph, right? And you do the similar thing. If you look at V2, you count A2 times n minus A2. It will be all the edges that involve V2. Then you make the sum, which is I from 1 to k, AI, n minus AI, right? And this sum have to divide it by 2, because each edge, if you think about it, each edge is counted twice. So it's again our double counting. Is it clear? So this is the solution. Great. Right? Right. So next, we have this definition. So this is actually the edge. So let's say this is the edge number of a complete k-partition graph. And the part size are A1, A2 until AK. So there's a question. So I don't know if I should mention this question later. So if you try to maximize this number, so I hope to find a k-partition graph, complete k-partition graph, by putting different part sizes. So it's a very interesting. It's just inequality in high school inequality. You should know. So if you try to maximize this, the maximum number will be achieved such that more or less each part has the same size. Okay, so it leads to this definition of TKN, which we call the Turan graph. So the Turan graph on it's a graph. This graph is on n vertices. Okay, so and the k parts. Okay, so it's a let's say it's on n vertices. It's a k-partite graph where each part has roughly the same size. So this really depends on if n is divisible by k. Maybe not, but that's why I say roughly. So probably you have some of the parts has a n over k floor, and some of the parts of size n over k ceiling. Okay, do you know this two notation? So it doesn't matter if you cannot divide exactly n by k, so you get probably an integer. This is the largest integer which is smaller than n over k. Okay, and then you probably want to add some vertex in some parts, and so eventually you get so let me say in other words, uh, so the size difference between two parts are at most one. Okay, you don't see two parts with size difference more than two. Okay, equal. Okay, greater or equal to two. So there are some larger parts, there are some smaller parts, but their difference is only one. So this is the best you can do if k is n is not divisible by k. So this kind of graph, if you think of it, it's a unique basically. So it's not unique. Probably you call different parts different names. Okay, so up to what we call isomorphism. So basically, it's a unique graph, and this graph is called the Chuan graph. So this graph turns out this graph is the so it turns out so this graph maximize the edge numbers among all k-partite graphs. So if you remember last time, again we have some trouble with my. Okay. So if you remember last time we talked about the extreme number of K3, remember? So it's basically n squared over 4. So if you remember this notation, so if you don't, it's fine. I will just mention this for 2 minutes for comparison. So this is the maximum number of edges for a graph which does not contain K3. Okay, with on n vertices. So a graph on n vertices which does not contain K3 has no maximum, at most this number of edges. And what happens that people try to generalize this result into this kind of result. So if you are looking at KR plus 1, okay, if you are trying to forbid, for example, K10, complete graph with R plus 1 vertices. So this is exactly the number of edges of T R N. Okay, so this is the Chuan graph. So basically, you draw. So you are trying to find a graph which does not contain R plus 1 as a subgraph. Okay, so then what you do is that you draw R parts more or less with equal size, which is this graph, Chuan graph, TRN. And you consider this complete graph, complete R partite graph. Okay, so it's so this graph, the edge number is exactly this. You can prove that if you have one more edge, you cannot find such a graph to forbid KR plus 1. So this is a famous Chuan's theorem. And then the proof is also a generalization of this proof. So I will not get into this. So maybe, I'm not sure, maybe in this course later, I will put one lecture on extremal graph theory. These topics are very interesting. Okay, so I think all these graphs are pretty natural. So you put a graph basically into R parts with equal size, and there is no edge inside, and all you see all edges between parts. So this is a Turan graph. Okay, so what's next? Okay, so I wrote something more in my notes, but it's fine. So basically, I mean, here there's a claim. I'm saying that this graph maximize. There is a claim maximize the edge number among all k bipartite graphs. So if you have a1 ak like this, right? This expression. Let's write this expression. So this expression star is the edge number L 1/2, a sum I from 1 to k, ak, and minus ak, right? So this is the edge number. And there is a hidden condition is that the sum of all ai, I from 1 to k, this is n. Okay, so this is the total number edge vertex number. Okay, so let's put them together. I'll ask, so what choices of AK makes this sum the maximum? Okay, what choice of A1 until AK will maximize this expression? So the answer is exactly they are roughly equal. Okay, so it's a to prove this claim here, you need to solve this problem. Okay, so I will not do this. Okay? It's not so hard because because you have to study this kind of expression. So this is just a constant. I mean, this doesn't matter if you want to maximize this. It gives you what is this? So if you forget this coefficient, it is I from 1 to k akn minus I from 1 to k ak squared, right? And here, what do you got? Here is n, and this sum is n again, so it's n squared minus I from 1 to k ak squared. So to maximize this expression, you need to minimize this expression. Again, with the condition that their sum is n constant. And you're trying to prove when they are roughly equal, this expression is the minimum. I mean, it's just a computation. If I don't remember if I put this in your exercise, but this should be something you should do once at least once. Okay. Okay. So next. So okay, in the next, I want to show you something that in history. I mean, it's a result. It's a very simple result, more or less simple result, but it was proven by Erdős himself. And I want to show you. I want to use. I don't know if I can achieve my purpose, but I want to show that how mathematicians are working. Okay, for example, you are really at the beginning of this area, so you don't know nothing. So you start to ask questions, and if you realize that some questions are really they are natural, but the difference between ordinary people and the great mathematicians is that they really sit down a little more time than other people. They don't usually they don't reflect more fast than other people, but they sit down more time than other people. So there is I think it's a very natural definition. What do we call a degree sequence? Do you agree this is a kind of natural definition? It's just D1. We already put it in the proof of our previous results. D3 and dn, right? For example, I mean, where di is just a degree of vi for some, you see, for some kind of ordering of vertices. Let's say v1, we already wrote this, okay? Vn. So you just write down all the vertices, and then you put its degree. So you get d1, d2, d3 until dn. The first theorem today, we just say that, okay, the sum of them is the 2 times the edge number, right? But now, okay, wait, we don't want to make sum. I want to understand the sequence in general. So I want to ask this question, what kind of sequence can be? So it's actually the question Erdős realized and solved it immediately. So he asked, what kind of sequence? So let me, okay, sequence. Okay, I think I need to do a more definition to make this precise. So this is a degree sequence of a graph. Okay, so another definition. It's actually equivalent definition. We call an integer sequence graphic. D1, D2, Dn. We call it graphic. If it is a degree sequence for a simple graph, okay, there is a little subtle difference. So if it is a degree sequence of a simple graph, well, we kind of don't want to allow double or multiple edges. Okay, so the question is, what kind of integer sequences are graphic? Can you simply write down a sequence such that you know it cannot be obtained from a graph, a simple graph? So can you determine this? So there is also another requirements. So since you write down a sequence, there's no difference if you order it. So I mean, if you reorder these vertices, you get a different ordering. So always we ask it has this kind of condition satisfied. I think we can agree that it doesn't really affect this question. It just make it more concrete. Okay, so take a sequence such that you put it in a decreasing order. So put the largest integer d1 and so on. Okay, put a sequence of integers with decreasing order, and then you ask, what kind of such a sequence? So which one could be a graphic, could be an integer, it could be a degree sequence of a simple graph. Okay. Yeah, do you agree? This kind of natural question. I think it's very natural. If you and I realize here there is a question here, and you sit down and solve it, it's a published paper. But it's, I mean, it happens like many years ago, 70, 80 years ago. But this was did by Erdős and one of his collaborators. So let me state a theorem, and next, and then we have an interval. So we next part I will prove this theorem. So theorem Erdős and the guideline. I think they together published a lot of papers, and this additional guideline theorem has all kinds of different theorems named after them. So okay, so let's put a integer vector. I call d bar. Okay, so let's say d bar equals d1, d2, dn. So it's an integer sequence with decreasing. Zero could be zero, okay, but decreasing is graphic if and only if two conditions. First of all, the sum is even. So we have seen this. We have to satisfy this, okay? The sum is even, okay? But this one is a simple observation. But second one is kind of is appearing from nowhere. So for all k, from 1, 2, until n. Okay, so for all k, you have this very strange inequality. J from 1 to k, dj. The sum of the first largest degrees, it's at most k times k minus 1 plus the sum from k plus 1 until n, the mean number. So I'll write two numbers and you choose the minimal one, or the smaller one, k and dj. That's it. So you have to verify all these inequalities. So in particular, d1 has to be smaller or equal than, okay, this is 0, okay? Because k equals 1, you have, this is 1 times this is 0. And sum, I mean, this is the special case. So j from 2 to n, the mean number of 1 and the dj, okay? And the d1 plus d2, it has to be smaller or equal than, here you have 2. So 2 times 1 gives you 2 plus the sum of j from 3 to n, the mean number of 2 of dj. Okay, you have to write down n similar inequalities. So if and only if all these are correct. Okay, so this is a theorem. Below is just an example. So this is a statement of the theorem. Okay. Okay, so we take a little rest, and we will come back in 4:10. Okay, 10 minutes after 4. Let me finish the recording. I will repeat our right theorem. Let me write down this theorem of Erdős and the guideline. The theorem. So a sequence D, D1, D2, and the Dn with greater equal than Dn greater equal than 0 is graphic if and only if 1, the sum of all numbers is even, and there is an inequality for all k from 1 to I think I should put n minus 1, okay? Because yeah, right. Oh, okay. And probably the situation of n is simple. So let's write it. So I from 1 to k di. This is smaller or equal than k times k minus 1. Okay. Right. So if I put n here, so this is the sum from all degrees, and this guy is n times n minus 1. So this is clear. But if we have a complete graph, only when you are complete graph, the sum equals n times n minus 1. So what is the total sum, total edge number of kn? N choose 2, right? So if I have a complete graph, the total edge number is n choose 2. So it is n times n minus 1 over 2. And this sum is exactly 2 times the edge number. Okay, so only when we are looking at a complete graph, this is equality. And clearly, for any graph, this is smaller or equal than it. So okay, so we can put n here. So for all this and plus the sum I from k plus 1 to n, the mean number of k and the di, this strange inequality. Maybe I put this star. I don't know. I like to use star. Okay. Okay. So the proof I think I will not give the full proof. One direction is very complicated. So let's first prove this direction, and the other direction is fairly complicated. I think I will only give the key idea, and ask you to think a little more after class. So so this direction I will give the full proof. So suppose we have okay, it's graphic. Suppose this guy is graphic, meaning that there is actual graph with this sequence. So we verify that this sequence satisfies 1 and 2. So 1 is clear. 1 we already proved. Okay. So we have to show that this kind of inequality. I want to explain using this proof to explain how this inequality come out. Why you have such a strange inequality. So suppose we have v1, v2, vn with degrees in some graph, okay, in some graph, in G, say, in graph G, we have these vertices with degrees d1, d2, dn with a decreasing order. So the left-hand side is the sum of, you see, the first k degrees. So we put A to be v1 until vk for any k, okay, fixed k. So we want to fix k and prove this inequality for any arbitrary k. So if k is fixed, we put A here, and the B is the remaining vertices. So we have vk plus 1, vk plus 2, and so on until vk, vn, until vn. Okay, so we have roughly how we can see this graph has a part A and a part B. So it's not a bipartite graph, it's any graph. But we want to group the vertices into 2 parts. And here, inside A, probably we have some edges also. Inside B also. So there is no, it's not a bipartite graph, okay? We just put 2 parts. So, and try to understand the expressions. The left-hand side. So what is the left-hand side? What is the sum I from 1 to k di? So for example, here we have v1, and we summed all the edges, right? So it has some edges inside A, and it also has some edges to B. We don't know, so sometimes we draw this kind of rough, very rough graphs to understand the graph theory, to make arguments. So when we draw it, we have to keep in mind that it's not precise. And for V1, for example, D1 is 5. In this case, we add 5 in this expression and we put this sum, right? And what is this sum exactly? So this is actually, if you it's look, so it involves all the edges which has at least one vertex inside A. But there are two situations. Some edges, for example, E here, is counted twice by this expression. Do you agree? So let's make a further. So this is a question. So if an edge E, let's write it as a V1, V2. I mean, it could be not necessarily V1, V2. Okay, so for example, V1, V2. Edge is here. So this edge, I claim that an edge V1, V2 is counted twice. By this expression. If both V1, V2 belong to A. Okay? Because this edge, if you draw it, when you are putting D1, you counted this edge once. When you are putting D2 here, you count this edge another time. Okay? And if an edge, let's write VW, okay, where V belong to A and W belong to B, this kind of edge, so no if, this kind of edge is counted exactly once. Okay, do you agree? This is a kind of a key observation of this proof, of this direction. What do you think? Okay, no response. I'll try to repeat. So let's say, I don't know, let's say let's put some simple example. Let's say here you have only 3. For example, here we have V2. Let's say V1, V2, V3. I don't know. So here you have many vertices. So probably you get something like this. This is right, and maybe something like this. Okay, and the 3 maybe something like this. Okay, so in this case, I want to put D1 plus D2 plus D3. In this very special case, D1 is 2, and the D2 is 3, and the D3 is 2 again. Okay, so it's some number, maybe 7. Okay, I claim that this edge, for example, V1, W1 is counted by this expression. And this edge, V1, V2 here, is counted twice by this expression. Because when you are put D1, this 2 is this edge and this edge, right? And when you count D2, so what is D2? D2 represents this edge, and this edge, these 3 edges. And in particular, this V1, V2 you counted twice because 2 vertices of this edge belong to A. Is it better? Okay, this is the only thing I want to say. So two sentences. First, an edge E1, E2, if both belong to A, is counted twice by this expression. And an edge VW, this kind of edge, V belong to A, W belong to B, is counted only once. So this guy, this sum implies that the sum I from 1 to K di, it equals twice the edge of A. So I write edge of A, meaning all the edge inside A. Twice edge of A, and once the edge between A and B. So this is what we have achieved so far. Okay. And then the remaining is actually simpler than the. I think so far the logic is full, is complete. Is you have to follow this, and the remaining are computations. Okay, so let's digest this again. So we are looking at this expression. Take V1, V2, etc. until Vk. So D1 is all the edges coming out of V1. D2 is all the edges coming out of V2. And we get this expression. But this is really a counting. So this counting, every edge here is counted twice. And every edge here is counted once. So we got this expression. And then what is 2 times EA? So A has K vertices. I think I just cleaned here. So what is the edge number of a complete graph on K vertices? What we call KK. So EKK is K choose 2. All the pairs are edges, okay? So it is K times K minus 1 over 2, right? EA is not necessarily a complete graph. But this is the maximum number of edges you can have. So this guy is smaller or equal than K times K minus 1. Okay, so EA is smaller equal than this number. So twice EA is smaller equal than this number. Now we are looking at EAB. Now double counting again. So to obtain this expression, I counted all the edges from A to B. It's the same. I mean, this expression is the same if I count the number of edges from B to A. It's the same expression. It means that all the edges between them. So either I count from here. I put every vertex and count how many edges it goes to B, or I list all the vertices in B and I count how many in every vertex here. I count how many edges it goes to A. So it's the same expression. So this is the spirit of double counting, right? So now to make this estimate, I do the other side. So I fix all the vertex. For example, here. So what are all the vertex here? You start from Vk plus 1 until Vn. Right? So it's a sum. The sum will be I from K plus 1 to N. And for each Vi here, I count. So let I equals from K plus 1 until N. And if I fix I, so let's look at Vi. So the question is, how many edges does Vi join a vertex of A? So question is, how many let's call neighbors of Vi in A. So vertex Vi has how many neighbors in A? First of all, this set A has at most k vertices. So this number is smaller or equal than k. It cannot be you cannot get a number of neighbors of Vi more than the size of A. Right? And also, you know the degree of Vi is Di. So it is also, I mean, at most, all its neighbors is in A. Then you are smaller than equal than this number. So you are this answer of this question is smaller than 2 numbers. So you just put the minimum of these 2 numbers. Okay, so this completes one direction of the proof. Okay, great. Yeah, that's cool. So sometimes sometimes it's way easier. I don't know. Sometimes it's way easier if you work it out. Sometimes I don't know. Sometimes these things depends on it's very mysterious. Sometimes it's easier to listen to a lecture to understand mathematics, but other times it's way better you work it out by yourself. You try both ways to make sure that you understand all the details. So this is a key theorem for today. Okay, I hope most people can follow this. And this is the easy part. Okay, so this direction is just you verify these 2 inequalities. You can I think, how do you feel? I think this direction seems easier, right? So how do you prove the other direction? One, you have a sequence which is decreasing, and it satisfies one, the sum is even. Okay, sum is an even number. 2, for any k you have this star, this mysterious inequality satisfied. By our proof, I think it looks pretty rough, but amazingly, any sequence satisfying this, you can actually construct a graph, making it graphic. And this all together, it becomes a beautiful theorem. So at the beginning, you make some guesswork. You write down some things, and then you realize, okay, it has to satisfy condition 1. It also has to satisfy condition 2. And then you wonder if these 2 conditions are enough. Any sequence with these 2 conditions are actually graphic. And you make this conjecture, maybe to yourself first, and you try to prove it. So the second part of the proof involves some. I don't know if this is actually the original proof, but now there is an algorithm given by 2 other people, which is Haiwo and Hakimi. Okay, so I think maybe the original proof more or less contain the main ideas, but this algorithm makes the organizing of the material clearer in some sense. So let's describe the algorithm first, and the proof, how the proof use this algorithm is it's another thing. So we have to pause a little bit to describe this. So let's look at a sequence satisfying the conditions, decreasing. Okay, only a decreasing integer sequence, non-negative. Okay, is satisfied with let's say with D1 greater or equal than D2 greater etc. greater or equal than Dn. We have a sequence with this property and also the negative. Okay, so this algorithm is this. So we obtain another sequence, what we call D prime bar, which is we delete the first D1, and we get D2 minus 1, D3 minus 1, until D1 plus 1 minus 1. And the next D1 plus 2 is kept. You don't change it. And then until Dn. So what we do is a little mysterious, but what's happening? For example, we have I don't know 4, 3, I don't know 3, 3. Let's write several threes. 2, 2, 1. For example, okay. So this is D. For example, I don't know if it satisfies our condition. Doesn't matter at this point. So I want to obtain D prime as first of all I delete 4. I get, and then the remaining 4 were 4 integers. I mean, the subsequent this is the first integer. It is number 4, and then I look at the second 4 subsequent integers. Each one of them I subtract by 1. Okay, so the first guy is deleted. Okay, I come, and then I get 2, 2, 2, 1, and the remaining doesn't change. Okay, do you understand the algorithm itself? Okay, so we try to understand the one object once at a time. So okay, after we understand this, we realize that this specific example is not decreasing anymore, right? So following this algorithm, we start with a decreasing sequence, but maybe we can arrive at a sequence which is not decreasing. So here we have 1, but it increased 2. So this can happen. Okay. So I didn't say anything about how this algorithm, we are going to use this algorithm. But this algorithm actually can change the property of the sequence. Okay, but this is just the algorithm. So we don't know how, so far we don't know how to use this. We will prove a proposition as follows. Maybe it's better I write a lemma. Okay. So indeed, D bar is graphic if and only if D prime bar is graphic. Okay, this is a lemma we will prove. So if we accept this lemma, we realize that this guy is not even decreasing. So it's clearly not graphic. So you can conclude that this guy is not graphic also. Okay, I think it's very interesting. This is not graphic. By lemma, this is not graphic also. To understand this this idea. So the effort is to prove this lemma. Okay. Yeah. So this is kind of let me explain something before let's explain something before I make actual proof. So the thing is that when you do proofs, what do we do? So there's a major technique called induction, right? So especially here we are doing combinatorics. We are doing graph theory, discrete kind of objects. Induction is a major technique because we are dealing with integers. We want to prove some property. We want P, a property, to be true, to hold true, to be true for all integers, right? So what do? We check n equals probably 1, and then we prove that if n is correct, then n0 is correct, then, I mean, if P is true for n0, then P is true for n0 plus 1, okay? And then together, we repeat, and if this is true, then it is true for all integers. And then, I mean, there is a kind of reverse process, which we call reduction. So in order for P to be true for n0, if I can prove that it suffices, it's enough that P is true for n0 minus 1. Okay, so I mean, it's the same thing, right? So, but this kind of thing we call reduction, very informally. Okay, so basically, you see, let's come back to this kind of depending how you understand this, it's kind of a induction or reduction process. You want to understand this sequence. You want to see if this is graphic, and then clearly we get some shorter and smaller sequence, and it's enough to check this guy is graphic. If we still don't know if the prime bar is graphic, we keep doing this. Eventually, it will become very clear. That's the idea. But okay, modulo this lemma. So the difficulty is this lemma. So this lemma. If you can prove this, I will. That's why I say I will not do all the details. I will prove this lemma, and the remaining stuff is left for you to check if you have the time. Okay, so let's prove this lemma. So if you remember this algorithm, then D bar is graphic if and only if D prime bar is graphic. So we prove this. Right. So to prove this, again, we need two directions. Right? I think one direction is easier, and yeah, one direction is very easy. So for example, let's check this direction. Let's put the easier, solve the easier first. So if D prime bar is graphic, is the degree sequence of some graph. Maybe we call H. Okay, so meaning that if I look D1 prime, D2 prime, maybe it equals D1 prime, D2 prime until DK, maybe let's put L prime. Okay, so is the degrees of maybe V1, let's write W1, W2 until WL. So these vertices of H. Okay, so maybe I don't know. I know that W1 has degree D1 prime. So I write maybe I write W1 here, W2 here, W3 here, and so on. And eventually I have WL. And maybe I don't know. This again we draw some very rough graph. We don't know. So maybe you W1 send D1 prime vertices to edges to other vertices, and so on. So we don't know all the information. So now what we do? We add a vertex W0, right? And let's say, let's choose, for example, D vertices, the first D vertices. So here we have W1 until, say, W3. Okay, so let's say D equals 3. And then I add W0 to W1, W0 to W2, W0 to W3. So what sequence do I have? Okay, it's not, so I put a D equals 3. I can do this only if 3 is greater or equal than D1 prime, okay? So I choose an integer. I choose integer D. In this case, it is 3, which is greater or equal than D1 prime. Okay? So then we get D, which is 3 here, and D1 prime plus 1, D2 prime plus 1, D3 prime plus 1, and the remaining doesn't change any. Here you have D4 prime and DL prime. Okay, this is the proof. Do you accept? I mean, one direction. Great, great. Okay, so this direction is a kind of it's constructive. You draw this graph here, and you know that the degree of W1, W2, W3 are the highest degree, and you draw this in this order, and then you try to draw this graph. So you add one new vertex, which you call W0, and this guy is exactly D bar. Okay. Okay, so another direction. So suppose now D bar is given. So you have D1, D2 until Dn. Okay, is graphic. Is graphic. So okay. So let me okay. So so it's maybe G is the corresponding graph. It means that okay, so G is the graph. This is the so whatever sequence is graphic is not necessarily you don't find a unique graph. You don't know this. Okay, maybe you have several, but G is one corresponding graph, some graph with this sequence. Okay, so I really want to find another graph starting from G. So maybe again for convenience, we have V1, V2, Vn like this. So the degree of V1 is D1 like before. But this is not enough. Probably I also want to change the shape of G to continue my process, because from here it's still difficult to get a graph with this graph degree sequence. Okay, good. So let's look at V1. So the purpose is that, let's say, from V1, we want to change the graph somehow. Change the graph G such that V1 joins the highest degree vertices. Highest degree D1 vertices. So I mean, in the beginning, this is not necessarily true. So let's draw some rough graphs. So this is a V1. So V1 is D1 is fine. It has the highest degree, maximum degree. So it may be sent to some vertices. But this is V2, for example. But I don't know that maybe V1 send a vertex to Vn. Okay, this is not very good for me, because if I delete this edge, you see, if I delete this edge, how the degree sequence will be changed? Dn becomes Dn minus 1, which this I don't like. Remember, I want the subsequent several vertices to be to have one less degree. So I hope V1 will join only the highest degree vertices. Are you guys still here? I mean, does it make sense? Yeah.
Can you repeat, please?
Huh? What was the question?
Can you repeat, please?
Yeah, I will repeat. So suppose in the perfect world, the first degree vertex, it joins V2, V3, V4 until this is V2, V3, V4 until Vd plus 1. Because it has degree D1, I mean. V1 has degree D1. In the perfect, I hope this happens. So for example, it joins V2, V3, V4 until Vd1 plus 1. And these are the remaining vertices. Here is the remaining vertices, starting from Vd1 plus 2 until Vn. Something like this. If this happens, I'm happy, because I want to delete V1 and all these D1 vertex edges. If this happens, I delete V1 and all its edges. And then what happens? So if I do this, the degree of V2 becomes D2 minus 1, right? Because this edge is deleted. V1 is deleted. And V3, its degree becomes V3 minus 1. Until here, we have Vd1 plus 1. The degree of this guy becomes D1 plus 1 minus 1. And the remaining guy doesn't change. And this is exactly D prime bar. And we are done, because we actually constructed a graph obtained from G by deleting V1. You get, for example, I call H, it realizes D prime bar. So D prime bar will be graphic. Only when I know that V1 joins the highest degree vertices. But now, in reality, it's a possibility that V1 joins, for example, the last vertex Vn there. If I delete it, I got something which is V1 minus 1. So it is not Vn minus 1. And maybe this V4 doesn't change. Maybe something like this. And we cannot delete V1. We can do it. I mean, we obtain some H the degree sequence of H is not this guy, which we hoped for. Okay, therefore, what we want to do is that we want to change the definition of the graph such that the first vertex V1, it actually joins all the highest degree vertices in the remaining vertices. Is it better?
Yeah, I think I get it now.
Yeah, that's great. I mean, this it becomes a little more involved. I try to. Okay, so once you agree, this is our goal. We continue. So the original graph G might not satisfy this, but this is something we hope for. We want to find a graph which satisfies this. Okay, maybe it has the same degree sequence. Okay, we start from a graph G with this degree sequence. We want to somehow change the graph G, but with the same degree sequence. And also it satisfies this property. And then we can safely delete the first vertex V1. So in order to do that, we have to analyze the situation that you see. We have to analyze the situation that V1 again. So let's say the following must happen. So again, V1 has the highest degree. I mean, the degree of V1 is D1. It is the highest number. It's the highest degree. Okay. And what I'm saying, the following is happen. So must happen. You have V1, it joins some V prime and some V prime prime, it does not join. And the degree of V prime prime is greater than the degree of V prime. Is that okay? I mean, if this never happened, we are happy. We already know that V1 joins all the highest degree vertices. Suppose V1 does not join all the highest degree vertices. Then it happens that some V prime is V1's neighbor, and some V prime prime is not V1's neighbor with higher degree. So this is just the negation of what we hope for. So if what we hope for does not happen, this must happen. Okay? Great. So if this happens, remember, V prime prime has degree higher than V prime. So there will be some vertex W here. So let's say, okay, so there is some vertex W such that WV prime prime is an edge. Yeah, I think, okay. And the WV prime is not. Is it correct? I'm saying that yeah. Okay, is that okay? So I'm using this. Maybe I call star star because V prime prime has more neighbors than V prime. And here V prime already used 1 degree here. So it has even less neighbors. So there exists some vertex W. We see this picture. V1, V prime, and the non-edge here, V prime prime, and some W. And here is another non-edge. All right? Okay, so I mean, because of this, because V prime prime has more neighbors, it has a larger degree. So we can choose some vertex W. It is the neighbor of V prime prime and is not the neighbor of V prime. This is crucial. Then we perform something called a two switch. So it's really simple. So we delete these two edges and we add these two edges. You see? So maybe I change the color. So this is a V prime. I draw here. I got a V prime prime. Sorry, I got something stupid. This is V1. Okay, this is V1. And here V prime it joins W, but here we delete two vertices. What's good about this two switch? The degree of every vertex does not change. So every guy, it has one more edge here and one less edge here. So degree doesn't change. No one has changed its degree. But after this two switch, V1 now joins V prime prime, which has higher degree. You see, which has strictly higher degree. And we finish one step. And then we look at this graph again. If this situation happens in somewhere else, and at most we do this for finite many of times, we can eliminate all such situations. So we will not see this happen again. So every time we found this, we do this two switch. So here I do it a little quickly. Later you think it with more details, okay? And then until one day you cannot do anything because this does not happen. So when this does not happen, it means that our V1 it joins all the highest degree vertices, and then you can safely delete V1 to get H, which has this D prime bar as its degree sequence. Okay. So this is the key proposition. So you prove that they are equivalent. They are equivalent. Yeah, great. That's something. That's a point. So, okay, it's not. If you eventually learn more in the area, there are tons of more complicated proofs. So this is something I think at the early stage has a fairly complicated arguments, and probably you can understand it. So okay. So I don't think we have enough time. I prepared one, I don't know, 2 or 3 small random problems in the notes. You can read after that. I think that's enough for today. We are over time. Okay. So there. Okay, great. So there is. Let me stop the recording.